Welcome back. Today I'm going to put together two of the concepts that we know from childhood, multiplication and division, but I'm going to slip in the middle of the concept of a limit. This is how we create the calculus. Now there's two breeds of calculus of this kind. There's the integral calculus. That's when we think of area to describe with approximations. The limit gives us the way to make the approximations. We could do this to make sure that we have an area for things that are curved and surface shapes. On the other hand, we have the concept of slopes or rates of change. This is when we think about how high up or down a function changes. For example, we think of the rate of change of gas prices over time. Does it go up? Does it come down? The way we measure those things is by attaching a single number, the ratio of the change in the vertical values to the horizontal values, and that can attach itself to a lot of significance depending on the story problems. Once more, we can think of an approximation problem within that space. We can try to decide whether we want to talk about the rate of change at any instant of time. There is no specific meaning to the instant of time, but what we can do is if an approximation can calculate a value that's accurate to within 8 decimal places, then we can assign that approximation the value of the instant of time. The philosophy there is that if we can only track information up to e decimal places, then what's the difference between knowing the rate of change at one e decimal place increment versus at an instant of time? Since we're not bothering to be any more accurate, we can't draw a distinction, and so we don't. We think of it as assigning a value to that instant in time. The two pictures that go with this are typically to draw some curve with area underneath it, and to draw some curve and talk about a tangent line. So let me remind you how we actually put this together. When we have this potential, we're simply taking the rate of change over the bottom times the rate of change over the top. That works perfectly with the distributive law of multiplication, which is why we attach the concept of area to the multiplication of length times width. For rectangles, that makes total sense. But this picture is not a rectangle, so the premise is that we have to subdivide it into smaller shapes where the areas are known, or perhaps the potentials if we want to keep track of negative signs. We could, for example, stuff smaller rectangles inside. It's not the total delta x that we had at the bottom that matters anymore. Rather, it's these changing differences of the different size boxes that we put underneath it. We're interested in a sequence that gives us the approximation at that n. For example, if this is our first approximation, then our n would give us the value of adding this area, this area, this area, and this area. So g of n, or g of 1, would be that total sum. If we wanted to make a better approximation, we'd move to g2. g2 would assign a different set of boxes, ones that fit more of the area. That'd be a second approximation. If we continue to make further approximations, the goal is that we would reach some limit L. When we say that the limit as n approaches infinity of g of n equals L, we're actually saying that to e decimal places, g of n is indistinguishable from L for all but finitely many values n. That is, our initial approximations we're allowed to throw away. We're, after all, making successive approximations. But if after some finite number of miscalculations, we can get within that margin of error, we call it the limit. This idea then allows us to take this e to any size we want, and some conceptual leaps are to imagine that e actually reaches infinity, at which point g of n equals L. This of course never happens, g never has a value of infinity defined, and n never gets there either. Infinity is always infinitely far away. We never reach or approach infinity. We simply remove finitely many counterexamples to any decimal place that you would think is in your way of an approximation. What's necessary to apply this process is to describe the way that we'll talk about the height of this rectangle as well as its width, but that's being updated with every approximation. So we should think of that not as a delta x with one specific value, but as a function that's parameterized by how many approximations we need. Now we know how to work out the area of these rectangles by taking the change in y times the change in x. These are all rectangles, they have that area. We add them up with this capital sigma. But because we want to be able to update this to whatever accuracy is required by our target, we want to be able to say that this width will keep changing. And it's therefore more like a function that describes how to assign a new width whenever you need it. Likewise, this sum is not a permanent sum of 1 through 4 boxes. The number of boxes will keep changing based on better approximations. So we changed both symbols from the Greek symbol sigma and the Greek symbol delta to symbols that are in our Roman alphabet. It'll be the letter S and the letter D. Now here the convention was to simply write down the things we were summing, but because that keeps changing, the better convention is to write down the domain over which we're summing. In this case, we're summing the x's from a to b. So we'll put those as superscripts and subscripts. Together, that's known as our integral, and we've had other videos on it. The integral is what we get when we take areas over specific rectangular shapes and combine them with successive approximations to get close approximations to curved shapes or any other shape using these rectangles. The notation is meant to inspire you to remember that it's a sum of small boxes. The little dx is replacing the capital delta x to remind us that we're changing the widths as we go along. And instead of a sigma to sum up all the sums, we're thinking of an s, because it's an ever-changing sum. The way we change it is hiding the limit process, which tells us to get accurate to within e decimal places, for all but at most finally many calculations that weren't quite as accurate. Now let's switch to the concept of slopes and rates. When I look at a function like this, it's tempting to imagine a rate of change as some kind of creature walking on the shape, for example, an ant. If an ant was to be walking on this part of the curve, it would be walking downhill. When it comes to this part, it would start to walk uphill. It would take some energy to go up. So we could see that the ant experiences a rate of change from downhill to uphill. But the question is whether an ant could detect the rate of change at any one moment in time. If the ant was to stay still, would there be any way for it to understand that the slope is up or down? It's impossible to answer. First of all, we're not ants. And secondly, because it's a conceptual question, what does it even mean to have time in the storyline? Oftentimes we use these words just to give us an impression of what's going on. The difficulty is assigning that a mathematical reason. It can be the case that you can fool yourself by giving yourself intuition based on experiences you've had, which bring in other factors, and the effect you're feeling is because of the other factors, not because of the factors as part of your story problem. So what we'd like to do is define a notion of an instantaneous rate of change, based solely on parameters that are mathematically valid. So, while we can't do an instantaneous rate of change, we can do the rate of change over two values. If I take the values a and b, and I go through this point that I'm interested in studying, I can see that at this point, the slope is downward. And because I've chosen 2 points on the curve, I actually have a unique line between the 2 points. That unique line has a slope, a change in y over a change in x. Now, what should I do if I want to make a better approximation? Well, one option is to get those 2 points closer together. If we bring those points closer together, we will change the slope. With this new yellow line, I've even moved to the other side, just to illustrate that there's no requirement that I be on one side or the other of the point. I am, however, closer. I've shrunk the gap. This should remind you of how we would shrink the gap in our integrals. We would make smaller and smaller widths. Here, we're making smaller and smaller widths as well. Our change in x is decreasing. Once we have a change in the x, we have a subsequent change in the y values. As that changes, that slope may or may not settle into a pattern. This is where we consult our limit. Our limit gives us a way to technically compute whether or not our pattern is emerging up to some number of decimal places. And if it emerges up to some number of decimal places for all but finitely many of the initial measurements, then we can say that up to rounding off that error, we can say that is the final answer. Notice it's not saying that we can actually carry out the slope process all the way to infinity. At the end, there would be no 2 points, and 1 point does not determine a line. What we are saying, however, is that the method of calculation for any 2 points getting closer and closer together might sometimes settle into a pattern that has a predictable outcome, L. That would be the slope of all the lines getting closer and closer together. If that happens, then we have all the data to define a line with slope L through that point. We have the point slope formula. So we may as well introduce the concept of the tangent line as being that line. It's the result of a calculation. When we combine the concept of this limit with successive approximations of a slope, and we get some particular value out, that is, if the limit exists, then we'll assign it a name. And similar to our integral calculus, we'll use a little dx for the change in the slope, and we'll use a little dy for the change in the height. So we now see that the rate of change combined with successive approximation gives us a new measurement called the derivative. If it exists, it's another powerful way to measure properties of a particular curve shape. It gives us a way to predict whether the ant at that point would think of it as going up or down, and by how much. What happens when this derivative exists? What it's really saying is that all but finitely many of the lines that get close together are in fact going to have the same slope up to e decimal places of precision. If you're not satisfied with e decimal places, go to e plus 2, 10, or any number of decimal places. The idea that the limit exists means that we can always update the number of decimal places and have a better approximation. We may have to throw out more of these initial measurements, but we'll still have all but finitely many of them within that margin of error. Standing back to look at this, you may feel like something is incomplete. Not only is this a pyramid without a top, but we can also observe that there's a mathematical relationship between multiplication and division. They are reciprocal to one another. And since both limits and integrals are simply using these two formulas together with successive approximations, it makes sense to predict that when you do one after the other, they should have reciprocal information as well. That is, if we take the integral of a derivative, we probably don't change anything. And likewise, if we take the derivative of an integral, that shouldn't change either. To do this properly together with the approximations takes a bit of work, and that's why it's called the fundamental theorem of calculus. Picking up on the concept that multiplication and division are reciprocals of each other, we see that delta y over delta x times delta x should equal delta y. That's on the macroscopic scale. On the microscopic scale, we want to get successive approximations that still rely on this formula, and we can do that. The fundamental theorem of calculus does this with its own notation. First of all, the delta y over delta x becomes our derivative, dy over dx. So we have that inside. Next, instead of working out the total area as a one big product, we think of this as multiplying a bunch of successive products that are then added together. So we have a sum of the inner parts and the widths that are being adjusted. Since this is an integral structure, that is, the whole is the sum of its parts, we expect that this is equal to the total change in y. The total change in y here is to go from a to b. The total change in y is the y value at b minus the y value at a. There's another way you might consider combining multiplication and division. That is, we could do the division after multiplication. That would translate into taking a derivative of an integral. That too is another form of the fundamental theorem of calculus. Let's include that one. This notation is slightly more nuanced than the one we did up here, but it's the same general content. The derivative here is being written on the outside, but we can think of it as dividing the whole by the change in x. What we do here is we start from a and we go up to the value x. The reason we go up to the value x is we're looking for the rate of change of the boxes that we're assembling in our sum. As we start from a and keep adding boxes this way, we'll see that we're adding more and more to the area. The quicker that area is changing, it's being measured by the derivative. And that is the same as the value of the y inside. It comes back to the formula that division of multiplication is the reciprocal. This is simply a glorified form of this formula, up to approximations, using this limit method. The fact that these two are reciprocal of each other comes down to the basic fact that multiplication and division are designed to be reciprocals of each other. However, we don't want to lose track of the fact that these are big steps in the process of problem solving. If we can attach meaning of areas and potentials to story problems, and likewise attach meaning of slopes and rates of change to other story problems, then what we can do through this simple mathematical relationship is draw deep relationships between seemingly different subjects. And it allows us to solve problems in new ways. For example, we might be able to produce instruments that can measure the rates of change very accurately. Think of a speedometer. Or we might be able to measure the outside of some boundary area. Think of a ruler. This gives us ways to measure integrals or derivatives that are quite different. Then when we approximate a new problem, knowing that we have this reciprocal relationship between integrals and derivatives means that we only need to know one of these two measurements and we can hope to solve for the other one without having to invent a new device, a new apparatus to pull off that measurement. Many of the story problems are still emerging. We're discovering new ways to measure rates of change and integrals inside of data of various sorts. But this reciprocal relationship will mean that if you've discovered it in one way, you immediately benefit from all those ideas in another way as well. And it'll be an exciting experience for you to discover what those two different meanings are and combine them into new theorems. All this has been written for the concept of what typically we think of as two-dimensional areas and two-dimensional rates of change. What happens if we need to update this for things like surfaces, solids? Many real-life scenarios involve multiple variables at once, which means that we can't simply say how is something changing over one specific x. It might be several x's, like an x and a y and a z. When we do this, we think of two variables feeding the last. For example, maybe we know y and x, and they parameterize z. That would give us something like a surface. This surface now is the values of z at over the grid points of x comma y. We could talk about the volume underneath there, and what we'd really be thinking about is approximating by a bunch of solid volumes, like rectangular volumes, little prisms. We could add up a lot of those boxes to get an approximation of the total volume. Like before, we needed limits to approximate various changes in the widths over here, but now also in the y directions. This calls for what's known as a double integral. In this situation, we could start from a to b and go from c to d. But we might as well start imagining that the boundaries are not always right angles. We could have a curved surface on the floor as well. So underneath this yellow surface, we could have some curved shape and then have this tube underneath there, which is rectangular. We stuff many of those underneath, and we successively update our limit to get better and better approximations. This double integral, therefore, should not really necessarily be between a and b and c and d, but it should now just be between some lower surface. We'll just call that d, the domain. Integrals like this are simply trying to measure the area underneath the shape, and we can even update these to have different kinds of measurements. For example, maybe we don't want x and y to be the way we stuff the boxes in there. Maybe we want something like polar coordinates or some other shape. So we start to change this and simply talk about this as a measurement. So we might use the letter mu for measurement. Now let's move to the derivative side. What if I have a surface and I want to talk about its rate of change? When we take a shape something like this and we plot a point down, we realize that rate of change is somewhat relative. If I'm here and I look side to side, I seem to be going up. But if I look a different direction, I seem to be going down. Since we have more directions, we have more ratios to take. Likewise, if we take successive approximations of both these ratios, we'll end up with multiple derivatives. It's become a convention to write the d as a slightly more scripted d to remind each other to look out for other derivatives. Otherwise, we might confuse ourselves and think there's only one. Since there are many variables, there are many slopes. Values, many variables gives us a larger version of volume. And yet, multiplication and division are still reciprocals of one another. So therefore, if we combine this information, we should in some way see some change that's reciprocal. What could be the reciprocal here? Well, there are entire courses called multivariable calculus that explore the many ways that this can happen. And roughly speaking, what they all do is get rid of one integral and one derivative in pairs. For example, if I have a double integral with a derivative inside, then I'll reduce it to just one integral. This version of the fundamental theorem of calculus, for example, takes on a few technical terms. Notice I've changed from dx dy to what I had before, a d mu, some kind of measurement of the space on the bottom. I've also denoted the boundary by this curly d. That's a symbol for boundary, and it reminds us there's a relationship between derivatives and integrals. What we see here is that we have a double integral, and the shape of this formula is one of the ways that we encode a derivative when we have multiple variables. So this is some measurement of volume overall. When we change over to here, we turn to what's known as a contour integral. We're moving along just the boundary of our shape. For example, the pink line at the bottom. And we're checking what the values do on the boundary. If we just inspect this for the algebra, this counts as one derivative, and it cancels one of the two integrals, leaving us with a single integral. That's the counting we expected. For example, if this is counting out meters squared, and this is counting out 1 over meters, then we've canceled 1 over the meters, leaving us with just meters. But there's a bigger change in the concept. Notice this one seems to depend on all the values over here, whereas this one only depends on the boundaries. This is no different than the fundamental theorem of calculus on an integral. A and b were the only things that mattered after we took the integral. But conceptually, what this is telling us is to think physically quite different. Whatever might be going on inside the interior ends up canceling out, and the only thing we need to know is what's happening on the boundary. This observation has changed the world of physics. We have learned to look for things on the boundary because that's an expression of a simpler system that we can possibly measure from other tools, simpler apparatuses. And this is only one of the many possible fundamental theorem of calculus generalizations. This one is known as Green's theorem, other ones are known as Stokes' theorem or Cauchy-Stokes. The world is still expanding this definition into new areas. The advent of data science has made very big spaces with many, many variables, and the rates of change that are going on there help us program neural networks. The updates that have to happen as we're training are dealing with how quickly we descend down slopes and how much total information is in the data sets we're studying. So the calculus lets you study it both ways. The key idea, however, is that you only need to study one to solve for the other because they're reciprocal relationships. So you look at your story problem and you decide, which side do I know something about? In a traditional take on calculus, you might find this theorem after several hundred pages of technical calculations. You may even have been introduced to the integral as first an antiderivative, then given some notion of a definite integral, the one that actually calculates area. By the time you get to fundamental theorem, the fact that it's the reciprocal of the derivative seems unsurprising. After all, it was defined as an antiderivative, then decorated by subscripts and superscripts. For me, that takes away from the simplicity of the idea that multiplication is the reciprocal of division, and that by adding approximation, we turn these into things that we can use on smooth and curved surfaces. This allows me to focus on the models that are important for calculus. What needs instantaneous rates of change? What areas are not easy to calculate as length times widths? This brings up the question of whether we should be doing some calculations. After all, this is the calculus. But here, I also take a different point of view. My point of view is that we can be assisted by computers. In fact, it's been that way since I was in high school. Today we can use a lot of free and special purpose software such as Mathematica, Wolfram Alpha, and ChatGPT to compute some of these integrals and derivatives directly. For example, we could say what is the integral from 1 to 97 of x cubed minus 2x times sine of x. We see that the integral is written correctly, and as we start to read, it computes the first term and then the second term. If we investigate further into the methods being used by these methods, we find that they're often far more involved and intricate than any of the methods you would see in a classical calculus course. Take a look at this blog post on the Stack Exchange website concerning these techniques. Even professional mathematicians would have no idea what most of these methods are. So it's a dwindling concern whether you really need to know how an integral is done, because it's no longer done the way you might have been taught. Learning how to compute various integrals can be quite exciting work, and you can get really good at it. There are even competitions on this, like the Putnam exam. And for many people, that's an introduction to mathematics. So I don't want to be seen as saying that that's not a useful topic. But I do want to say that we want to avoid the situation where we try to train people to do party tricks. That is, we don't necessarily need to compete with machines. They're made for calculation. My recommendation is this. Focus on when an integral and a derivative is important. Focus on what information is accessible to the data sets you have. Can you measure rates of change? Can you measure potentials? Whichever ones you can measure, try to find the other ones. Also focus on the interpretations. Does your data seem to be changing in a way that's integrable? Does your rate of change seem to be approaching something that has a limit? With these words, you can start to decide whether this kind of mathematics is even appropriate for your story problems. Computers are really good at spitting numbers out, but they're not really good at telling you whether those numbers mean anything. Your job is to stand in the middle and say whether this machine learning algorithm gave you something useful. If you don't appreciate what these are trying to measure, there's no way the calculation is correct. You'll definitely consider information that comes out of this system as more meaningful once you appreciate what it is about. So, attach the significance of these methods to whether your model is actually about integrable or differentiable systems. If it's not, then question the use of these algorithms by any method, either by hand or by computer. As a final caution, don't let me stand in the way of your fun. If you enjoy taking integrals and finding lots of clever tricks to do it, or taking derivatives, go for it. Those are techniques that might actually serve for you in a lot of different situations. I'm no expert in pedagogy. Perhaps going through that process will help you become a better reasoner. But if you're in a pinch and you need to get some understanding quickly, I recommend that you not perseverate over the calculations of calculus. Machines are really good at that stuff. But perseverate on what these things mean to the story problems you're after. If you want to understand the ethos of calculus, it's to take multiplication and recognize its reciprocal as division. Combine that with approximation and make together a pyramid that gets you to the place where you can take measurements on one side or the other and benefit from that result. While the precise forms are delicate and take years to master, with the help of AI and reading resources, you'll be able to match some of your problems to these things faster than you realize. Don't be scared of these symbols. The fact that they've been on the background of a lot of movies doesn't mean they're actually any harder than your good old-fashioned multiplication and division rules. Until next time. That's how you take care of your chalkboard.